Okay, welcome back. So we had concluded the last lecture with continuity equation, and I told you how excess carriers decay, right? And we derived the continuity equation, and we told what the importance of this equation is. That is to find out the excess carrier density, because that will give you the the diffusion current. And drift current of course depends on field. For that also you need the carrier concentration, right? So it's very important to understand continuity equation. That was the main essence of the last lecture, and I told you that today we shall start p-n junction, and maybe before that we can give a couple of examples of how the continuity equation is useful, right? And once we start p-n junction, then many other devices will become very easier to understand, like BJTs or solar cell photodetectors, LEDs. They are all essentially p-n junctions. And eventually also we will touch base with MOSFET, because MOS transistor is the classic device that we have to learn in this course, right? And we will always take take examples of realistic devices, real technologies that are going around, so that we are able to calibrate ourselves as to what we are studying is in relation to what actually is around in technology. Okay, so we shall begin from the continuity equation where we left in the last class. We will come to the whiteboard now. So if you recall, in the last class I had written down the continuity equation. If you recall the continuity equation, it was dn, the second derivative of excess carrier with respect to position, plus the optical generation rate minus the excess recombination that will take place is equal to 0. Now let's pause for a minute and try to understand again. Okay, this is your optical generation or any excess carrier generation that is happening, mostly by optical excitation. So if you are shining light, then you will generate some excess carrier. That is what this rate means. Okay, this is basically meaning how the carriers are recombining and decaying. If you recall Shockley-Hollerith statistics, because of traps or because of electron hole recombination, you will always have excess carriers will recombine. Okay, electrons and holes will recombine and getting lost, and that recombination is captured by this thing. Always remember that recombination rate is delta n by t. Of course, if there are holes, then it will be delta p by tau, and this tau is essentially the lifetime with which they are decaying. Okay, the excess carriers are decaying, and that's why there is a negative sign here, because it is losing. The carriers are recombining and losing. There is a positive sign here because carriers are generating. They are exciting and they are generating optically, for example. And this term refers to essentially the particle flow rate in and out, right? The flow rate that is out minus the flow rate that is in. Essentially it tells you the flow, that in a particular sample, carriers are coming in and going out because of current, and that rate build up is basically captured by this. It's a second derivative of the excess carrier, and there's a diffusion coefficient of course here. We had neglected electric field in this equation. I told you if you put electric field, it becomes little bit more longer. We are not discussing that in the course right now, but if it is necessary, we will discuss that as and when the necessity arises. Okay, now again let's take a minute to pause and ask ourselves, this is a continuity equation by the way. Okay, now the question that we should again ask is, what is the use of this continuity equation? Is there any benefit to actually understanding and deriving this mathematics of this equation? Yes, because the continuity equation, and I hope you remember the derivation, the continuity equation essentially enables us to estimate delta n or delta p, which is the excess carrier concentration. Okay, and you will ask, why is it excess carrier necessary? Excess carriers can be there in a semiconductor either when you apply a voltage. For example, you have an n-type semiconductor. Okay, it's equilibrium. But the moment you apply a voltage, you are actually injecting carriers. No, you are injecting because there will be current now that is flowing, and at moment current is flowing, there is an injection of carrier, right? Then an injection of carrier from, this is a battery for example, it will inject carriers, no, either electrons or holes, right? That injection of carriers leads to excess carriers in the sample, right? So in equilibrium, for example, this sample had a concentration of 10 to the power 17 per centimeter cube, but once you apply voltage and current flows, then excess electrons and holes are injected, right? So that excess carrier comes because of either this, or it can come because of optical shining. Okay, it can come because of optical shining, or it can come because of many other reasons. So whenever there is an excess carrier, which is delta n and delta p, your continuity equation helps estimate that excess carrier concentration. And once we know the excess carrier concentration, we know the current. For example, diffusion current depends on q dn, for example, delta n by delta x, right? So that is why we need to know the excess carrier to estimate current density, because only when we know current density we shall be able to analyze the device performance. Okay, we shall be able to analyze the device performance. That's why continuity equation is so important in this context. Okay, now when you solve continuity equation, there are different boundary conditions that you have to look into depending on the situation. For example, if I take a very thin, let me not draw it here. Suppose I take a very thin slab of semiconductor. It's very thin. Okay, it's very thin and it's uniformly, say, n-type dope, for example. I'm shining light of wavelength lambda that is absorbed here completely. So around everywhere the absorption is uniform, and I'm shining everywhere. So everywhere in the sample the absorption of the light is uniform. Okay, the absorption of the light is uniform. And so when you absorb light in a semiconductor, what will happen is that you of course know that excess carriers are generated. So electrons from the valence band will get energy because of the light to go to conduction band and give these electrons, leave behind holes. So essentially you create electron holes pairs. You create electron and hole pairs when you shine light that is absorbed. Okay, the light has to be absorbed, of course. So here I'm assuming that light is all absorbed. I told you once that for light to be absorbed, the energy of the photon h lambda by c has to be greater than or equal to the band gap. So the lambda has to be less than or equal to your hc by lambda. So hc by lambda has to be greater than or equal to the band gap. So lambda has to be less than or equal to hc by eg. So only in that condition your light will be absorbed. So once your light is absorbed, you create electron hole pairs. When you say electron hole pair, this actually means delta n and delta p. You are creating extra electron and extra hole, and always excess electron is always equal to excess hole, because for each electron that is going you get a hole here, right? So that has to be always equal. So when you absorb uniformly here, then there will be no diffusion, because everywhere the carrier concentration, excess carrier concentration delta n delta p is same everywhere. And then you can solve the continuity equation there to find out how it decays with time, for example. So as long as it is shining, what will happen? You recall the continuity equation. The continuity equation is q dn delta square n by dx, okay, plus gl minus delta n by tau is equal to 0. Now see, everywhere it's uniformly shining, so the excess carrier concentration everywhere is the same. So there is no gradient of the excess carrier. If there is no gradient of the excess carrier with respect to distance, this is distance, right? Then this quantity becomes 0, because over any distance x it is the same. So what happens is that then I can solve this equation, and I'll just say that from this I can say the optical generation rate is equal to delta n by tau. So the excess carrier that is generating delta n or even delta p is equal to tau times gl. So that is the excess carrier that is generating uniformly. So optical generation, the light that you are shining will have a given gl. So it might be 10 to the power 15 per centimeter cube per second. So that you multiply with the lifetime. It's the lifetime of set nanosecond or whatever. So you will know how many excess carriers you are generating essentially. This is unit is per centimeter cube. Now the moment the light is switched off, okay, if you switch off the light, for example, then the carriers will decay with time, not distance. Everywhere it was uniform, no? So carriers, the excess carriers will decay with time. And by doing this measurement, actually experimentally you can do the measurement of the carrier lifetime. So once you switch off the light, what will happen? The excess carrier that was there in the sample, they will decay. They will decay with respect to time, not with position. Why? Because everywhere else the light was shining equally. So everywhere the excess electron hole generation density is the constant with respect to distance. So there is no diffusion or anything, but with time it will decay. So what will happen? What will happen now? So you have to solve the continuity equation again, right, with the boundary condition that exactly when your light is switched off, at that moment at t equal to 0, suppose you have switched off the light, at that moment this was the excess carrier, because this was the uniform excess carrier density. So the moment you switch off the light, you get this was the excess carrier that was preserved, that was persistent there. Now switch off the light, so this excess carrier will decay from this value, which means if I plot delta n at any point I can take, it is the same with respect to time. Then at time t equal to 0, when I switched off the light, this is the excess carrier that was there. This point is actually this point is actually tau times gl. This is the extra value here, and it will decay from here like this exponentially. It will exactly like go asymptotically to low value here. So that will decay exponentially. And how do you actually do that? You solve the continuity equation again with that boundary condition. So now you know the continuity equation is again dn delta square n by dx square plus gl minus delta n by tau. Actually we put this as 0 because it was in steady state. That's why we put this in state. We put this as 0 because if you recall the derivation, this is actually not 0. We put it 0 because in steady state it is 0, but now it is not steady state when you switch off the light. Actually this was delta n by dt. It was with respect to time. This is again 0 because there is no change in the x, everywhere it's same. So essentially what happens is that you have gl, right, minus delta n by tau is equal to delta n by dt. But this will be 0 now. Why? Because you have switched off the light. You have switched off the light, so the optical generation goes to 0. So essentially it is like some constant times y is equal to dy by dx. Excuse me. So you can find out the solution in the appropriate boundary condition that delta n is t equal to 0. At t equal to 0, okay, at t equal to 0 delta n, it was tau into zl. So if you solve that, then you will find out delta n as a function of tau will be actually tau gl plus some constant, and exponentially it will decay minus t by tau. So as I told you, it will decay exponentially like that, e to the power minus tau by t. So if you switch off the light experimentally and you measure the carrier density, you will find an exponential decay. If you take the exponential decay and you fit it, I am talking about experimental measurement, then you will be able to find out the carrier lifetime tau. That's how people find out the carrier lifetime. So this is one example of how you can apply the continuity equation. This was just a block of semiconductor without any bias, just very thin, exposed to light completely. Similar exercises can also be done in some other cases. For example, if you have a semiconductor and this side is put to ground and your light is shining only at this side. Your light is shining at this side, so electron hole pairs are generated here in very large quantity, but then in a few nanometer here, electron hole pair will be all absorbed and generated. Light will not penetrate deeper because light will be absorbed, and then excess carrier here will generate, they will decay, essentially they will decay. So for that also you can solve the continuity equation. I will leave that as an exercise. You can solve the continuity equation, you can find out how the carriers are decaying. This is with respect to distance, this is a sample distance, so that in different circumstances you will be able to come up with a solution once you know the continuity equation, once you know the boundary condition. So armed with all these fundamentals and basics, now we are able to go into the discussion of p-n junction. Okay, and p-n junction will depend heavily on the concepts of carrier decay. Carrier recombination and decay is the same thing. Carrier decay or recombination, whatever we have learned till now. Continuity equation, it will depend heavily, right? It will also depend heavily on the basics of your doping, of your density of states that you learned, of your Fermi function and other things that we had learned, right? It will depend also on your current flow, your drift and diffusion current, right, will be very important in this, right. So p-n junction will now involve many of these things, and also everything that we have learned till now will be used. So it is important that we pause here and we basically make sure that whatever we have learned till now, we are in sync, we are not able to lose, we are not losing focus. Okay, whatever we have learned till now, we should be able to recall as and when it is necessary, because now we are going to study p-n junction. Okay, and p-n junction, as I keep telling, will be the building block of BJT, HBT, they are transistors, of LED, of solar cell, of photodetectors, okay, and many other applications. Actually many other types of transistors also, various other types of transistors like IGBT, HBT, they all will depend on p-n junction. Even MOSFET, you will always need the basics of p-n junction anyways, and MOS, MOS capacitance and all. So basically p-n junction is like the foundation on which many of the things are resting. So we will have to really carefully look at p-n junction. So I am hoping that till this point in time, whatever we have had studied, things like excess carrier decay, continuity equation, how we solve the continuity equation, how we derive the continuity equation, these are all clear to you. If you remember the long diode, the short diode things that I had discussed with you, the derivation of the continuity equation. Shockley-Hall recombination was more about traps, how they recombine, the carriers will recombine with the traps, we hope you remember that those things, and we had also done some simplified examples of that. Trap dynamics and all, we had studied that. I'm just recapping whatever we had learned in the last few lectures. Einstein relation we had derived, and this is very important. Einstein relation essentially was the diffusion coefficient by the mobility is equal to kT by q. So this will become very handy, very useful in whatever we are going to do in the next discussion of the p-n junction, so that we should not forget that. We had also discussed about drift diffusion basics, the derived expression for diffusion current. I also had derived expression for the drift current. Before that, we had discussed mobility, how mobility is affected by carrier scattering from the impurities, from phonons, which are nothing but lattice vibration. I also told you the definition of mobility. What does mobility mean, right? What is electron velocity, how electron velocity saturates, how mobility changes with temperature. Electrons have their own mobility, holes have their own mobility. Mobility of silicon, electron in silicon, for example, is 300. Mobility in graphene or other material, could be even 100,000 or a million at low temperature, for example. It depends on the material. And I also told you that velocity does saturate, all these things the carrier transport is discussed. So, and that's how we discussed in the last few lectures. And of course, before carrier transport, we had gone through other things like about your carrier statistics, density of states, doping, incomplete ionization, heavy doping effect, Joyce-Dickson equation, partial or incomplete ionization, heavy doping effects like band tail. At very high doping, the band gap will become lower, and so many things were discussed actually. So now we are armed with all of this, and we believe that now you are capable of finding out about the details of p-n junction. So here we'll begin the p-n junction fundamentals. Okay, we'll begin the p-n junction, and we'll continue. The next few lectures will be on p-n junction. So there's nothing to be worried. So we'll go slowly. We'll make sure that everything becomes clear here. So essentially, p-n junction is very simple. You for example take an n-type material. Okay, you suppose you take an n-type material. Okay, electrons, there will be majority of electrons here, right? And then you take suppose a p-type material, right? You take a p-type material, so you're doping it acceptor density, some doping is there, and consider these are light or moderate doping. So there is no heavy doping effects like Joyce-Dickson and all. That is one approximation, one assumption we are taking. One assumption is that there is 100% ionization of the dopants. So there is no incomplete ionization or no partial ionization, which means if I am doping it 10 to the power 17 of acceptor ions, then I am going to get exactly same number of holes. There is no incomplete ionization. That is an assumption. And the third assumption is that these are all at room temperature and equilibrium. So there is no light shining, no magnetic field, no electric field, nothing. Just these are the conditions that we are going to assume. So I'm taking an n-type semiconductor. Okay, I'm taking an n-type semiconductor. I'm taking a p-type semiconductor here, and the p-n junction will essentially form when I join them. Okay, when I join them. So what will happen when I join them? Now, how do I join them physically? That is a different question. I don't put any glue or Fevicol or something to join them. That is not how it is done. We'll come to that fabrication later when it is necessary, but suppose we are joining them. What is the thing that will happen when we join them? See, this side is p-type doping, so there are many holes. So there are very few electrons on this side, which are called electrons are minority. So electrons are very low in concentration, that you know. And similarly on this side, the other side, because it's n-type dope, holes are a minority. That means hole concentration is very low. Now you recall what is diffusion? Diffusion is whenever there is a higher concentration of something on one side and a lower concentration of something on the other side, the species will try to move or diffuse from the region of higher concentration to a region of lower concentration. So there are more electrons on this side, there are very few electrons on this side, which means electrons will try to move from here to there, right? Because unless you join, they will not move because there is a gap of air here, but once you join, they will try to move. So let's go to a new page and let's draw it again fresh. For various reasons, it's the same if you either take an n and p, n is on the left side, p is on the right side. It's the same as you taking p on the left side and n on the right side. but it so happens, and everything remains same of course. I mean, if I join this, it's the same as this, whether it is left or right doesn't matter, but conventionally we define this as the positive x direction. So it will be good if the current is flowing in the positive direction, then the analysis becomes generally easier. I mean, if the current is flowing in the negative direction, everything does nothing change, it's just an orientation difference, but then everything is, we have to put a negative sign because it's a negative x direction, or we have to define this as positive x and this as negative x, which becomes little strange. So there's no physical difference at all, but to make things simpler, we'll go with this this particular configuration, because then electrons actually the current will basically be flowing to the right, that makes sense, I mean, better. So I'll take a p type material and I join with an n type material here. I'll take a p type material, I join with an n type material. I told you there are excess holes here, there are very few holes here, so holes will try to diffuse from p side to n side because there are very few holes on the n side, and electrons are majority on the n side, but there are very few electrons on the p side. So certainly electrons will try to diffuse to the p side. Now electrons are diffusing to the p side, or holes are diffusing to the n side. They will meet at the junction. Because, and why are they diffusing? Because there are very few holes on the n side, very few electrons on the p side. They will diffuse because they know the concentration gradient. When they diffuse, holes are diffusing to the n side and electrons are diffusing to the p side. While they are diffusing physically, they will actually meet at the junction. They will meet at this junction, and the moment electrons and holes meet at the junction, they will recombine. And when they recombine, basically electrons and holes have recombined, they are gone, right? They have recombined, they have vanished now. What leaves behind when an electron and a hole will recombine? See, this entire p type region, let me draw again. This entire p type region is actually filled with Na minus. Okay, that is ionized, negatively charged ionized acceptor. I told you, when an acceptor atom accepts an electron, because it gives away a hole, right? It gives away a hole. That means it accepts an electron. It becomes negatively charged. So the ionized acceptors are negatively charged when they have given their holes. Similarly, on the n side, ionized donors are positively charged because they have donated the electron. Now they are left with a positive core. So the whole thing is filled up with positively charged core. Whole thing is filled up with negatively charged core. But because there are mobile electrons or mobile holes here, which are positively charged, and there are mobile electrons here which are negatively charged, so they exactly balance this. This exactly balance that. That's why the total charge is 0. Now at the junction, let me go to a different page. I told you that holes are trying to go to the other side, electrons are trying to come to the other side, and at the junction when they cross, they will recombine here. And the moment electrons and holes are recombining, why they are recombining? Because they are moving to the other side. No, as soon as they recombine, they are gone. What is left behind in this region is ionized acceptor and ionized donor. Ionized acceptors and ionized donors are left behind here, because the mobile electrons and mobile holes have now vanished. They have not vanished from here, they only have vanished near the junction. How near the junction? We'll come to that. I mean, what is the extent around this? Is it like nanometer on both sides? Is it like hundreds of nanometer on both sides? We'll come to that. Now you might say that holes will still, fine, that is fine, but holes will still try to keep coming to the other side from here. Electrons will still try to come to the other side from here, but no, that will not be possible, because as soon as they leave behind a positively charged and a negatively charged core here, this establishes a field. This establishes a field, electric field, and that field will oppose any further diffusion of electrons or holes from the other side. That there will be a field that will develop as soon as they recombine and leave behind a positively and negatively charged ionized cores. That field will oppose any movement of holes. The holes are trying to move here, this field will oppose that. Okay. Similarly, electrons are trying to move this side, diffusion, that field will oppose that. So that field will ensure that no further electrons and holes can now diffuse and it will reach equilibrium. So, essentially in equilibrium what it will look like is that there is a junction here, of course, some part around the junction like this, some part around the junction there is this positively charged core, negatively charged core that has been left behind because of the electrons and holes being mobile, they are combining. Here you have lot of holes, lot of equal number of Na minus also. Similarly here you have lot of electrons and equal number of positively charged Nd also. So, these are all balanced. So, the total number of electrons here is equal to exactly the total number of Nd plus. So, it is charge neutral, here also it is charge neutral. Okay. But there is a field here, that field will now oppose, that field will oppose and make sure that no more holes can come, that field will also oppose and make sure that no more electrons can come. So, it is now in equilibrium, it is now in equilibrium. Okay. There is no current flowing. Initially when they combine you might think that there is some current flowing, but that is a very quick process where little bit of electrons and holes have moved and basically balanced, and now there is no current, actually there is no current flow now. So, this is equilibrium that has formed. Now, we have to be more careful in trying to understand each and every step that will happen here. So, for example, this was p type. So, that means there is a Na that you have doped here, and this is a junction, this is x equal to 0. Okay. This is very long junction. So, this is very large. Okay. And this is Nd doping that is here. So, it is a n type here. Once you holes move from this side to that side and they are recombined in the near the junction, what will leave behind here, when I say this is the junction that has formed here, what leaves behind here is negatively charged ionized cores, Na minus. This Na minus is also here. Okay. But those are balanced exactly by the holes that are there, the holes that are there. Okay. Similarly, there are Nd plus here, but those Nd plus are balanced by electrons that are here. So, it is all in equilibrium anyways. But over in this area, in this n type area, and over in this area, the mobile electrons and mobile holes have recombined and they have vanished. Okay. So, what has left behind is a positive negatively charged ionized core here, and here they have left behind like a sheet of positively charged dopant here. There are no mobile electrons, there are no mobile electrons. So, this region that has formed, and there is a field here, now I keep telling you there is a field here which will oppose any movement of electrons and holes from either side to other side. Matlab electrons from here to here they will be blocked and holes from here to here will be blocked. So, this particular around region that has formed, that is called depletion region. Why is it called depletion region? The word deplete means that there is nothing, it is depleted. When you say that particular area is depleted of mineral resources, it means there are no mineral resources in that area. When you say that lake or that river is depleted of water, it means there is no water. So, when I say this is depletion region, it means this is depleted of carriers, mobile carriers. Okay. Depleted of mobile carriers. What are mobile carriers? Mobile carriers are electrons and holes. So, electrons and holes are not there because they have recombined. What has remained there is immobile negatively charged and immobile positively charged core. This region has no free electrons, no free holes, and any further movement of free electrons and free holes from both sides are blocked. So, this region is called depletion region because this is depleted of carriers. There are absolutely no mobile carriers here, that is the approximation, it is called a depletion approximation, and there will be a field here now. Okay. Now, how will in this once you have joined this thing and you have understood that this is formed, how will the energy band diagram look for this same? You remember energy band diagram, conduction band, valence band, Fermi level. How will the energy band diagram look for this? That will tell us exactly many of the things that we want to understand in the PN junction. Okay. So, we will take up that in the next class. So, here we will wrap up the today's session here and the introduction of PN junction, right, and we had introduced PN junction, and before that we have solved examples of continuity equation, if you remember. Now, we have introduced the concept of depletion region and how electrons and holes diffuse and they recombine and so on and so forth. Next class we shall actually try to draw the energy band diagram of the PN junction, and so many things will become clear the moment we draw energy band diagram. The conduction band, valence band, Fermi level, if you recall, we will join that diagram from p side and n side and see what happens. Okay. So, we will end up the class here. Thank you for your time and we will catch you in the next class. Okay.